we are discussing about the feedback amplifier. So in that feedback amplifier, we have seen the feedback amplifier circuit. So in that feedback amplifier, we have seen what is the general feedback structure of an feedback amplifier, and how the general feedback structure on employing the feedback. So how it is going to how we are going to get the gain with feedback. So because the gain is going to be a reducing one, and we have obtained the gain expression as well in the previous class. So this is a gain expression, so which you can see over here. So this is a feedback with the gain. So the gain is nothing but the output voltage, output signal to the input signal source. So we are going to take, and the x naught by x ness. So in this, upon employing the feedback network, so whatever the gain which you are going to get, so that gain will be considered as the gain with the feedback and denoted as AF. So A suffix F, so which is nothing but gain with feedback. And we have seen that the gain is feedback gain you are going to get as A over 1 plus A into beta. So this is a gain with feedback, and we can say that on employing the negative feedback, the gain of the main amplifier is going to be reduced by a factor of 1 plus A beta. So this is the main amplifier gain. So that is A. It is going to be reduced by a factor of 1 plus A times of beta when you employ negative feedback. So this is how it is going to work. So it is the only disadvantage or the drawback which you are going to have, which you are going to see or observe in the case of gain with the negative feedback. So all five advantage is the limiter. So these are the five important properties of the amplifier. So negative feedback amplifier. So on employing the negative feedback, you are going to get these five benefits. So over only one drawback is nothing but the gain. So gain is going to reduce in this case. So the gain with feedback you will be having the reducing by a factor of 1 plus A into beta. So where A into beta corresponds to the loop factor. So there is loop gain. So on employing the negative feedback, it is going to reduce by this fashion. So this is about the negative feedback, and we have also found out the relation that is going to have between the feedback signal as well as the source signal. So you can see this is the XF is nothing but a feedback signal, and XS is nothing but a signal source. So we know that what will be the impedance, what will be the relation. So XF will be equal to XS, and you can say that is by a factor of A beta divided by 1 plus A into beta. So A into beta is nothing but loop gain over 1 plus A into beta. We also know that the A into beta will be very much greater than 1. So obviously this plus 1 is not going to have any impact on the denominator. So if you see the expression, so the XF, so that is the feedback signal will be almost equal to that of XS. That means signal source. So source signal whatever it will be there, so that much only the XF signal will be XF, that is the feedback signal will be almost equal. And if you consider XF as well as XS both are nearly same, then what will be the error signal? Error signal will be almost 0. So the almost it will be equal to 0. So this is how we are going to get the relation for this one. So XF and XS. So by through the previous expression equation 5.5, so we will come to know that the feedback signal will be almost equal to that of the source signal, and hence if we consider what will be the error signal, so error signal will be very much almost equal to 0. So from that we can say that the obtained the relation between xi and xs, and we have obtained that xi will be equal to xs into 1 over a into beta, and we know that a into beta will be very much greater than 1, and if you see 1 over a into beta, so obviously the gain, so that is so kindly mute yourself. Okay, so xi is the limit input signal. So input or else we will be calling it an error signal. So error signal will be almost 0. So what will be xi? Xi will be equal to, we have derived that xi will be equal to xs minus xf. Since xf and xs both are nearly same, so you can say that xi will be almost equal to 0. So these are the relationship between the different parameters in the feedback structure. And now we have seen that in the previous class also. So gain d becomes desensitive. We are going in detail how the application of this negative feedback will have the advantage. In the first thing is that we have seen that again the desensitize the gain. So desensitize the gain means so uh, it is going to the main amplifier gain will if there is any drastic change in the main amplifier gain also. So through the feedback structure only I will explain. So if the say if feedback structure if it is not there, so if the feedback assume for a time being, so that feedback structure is not there, is not present in the structure, then it will be considered as what? So open loop amplifier. Okay. So open loop amplifier under, so you will be having signal source will be there, so amplifier will be there, so this amplifier gain will be considered as what? Open loop amplifier, right? Open loop amplifier, and the gain which you will be getting with respect to x naught by xs is nothing but what? So xs x naught divided by xs, which will be the gain which you will be getting from the open loop amplifier. So for this amplifier, so if you change the component value, or if it is affected by the temperature variations and all, it will happen means, so obviously it is going to affect the output voltage, output signal. So it will be very much sensitive to the external environment. So when it isn't connected without any feedback, if it is employed, so it will be having a direct sensitivity will be more. So because of variation in the changes in temperature, it will cause the variation. So the gain is also going to have variations will be there. But now when you employ the negative feedback, so now the circuit will be having this much. So when you employ the negative feedback, that is when you employ this feedback into the main amplifier circuit, so this feedback will going to make this main amplifier desensitized. So even if there is any variation, small variations that is going to be observed, so in the main amplifier also, even if there is small change, that is not going to affect with respect to beta. So that means the feedback network is not going to see drastic change, will be not you cannot able to see in the output for a small changes in the amplifier. So that thing we are going to demonstrate over here. So how we are going to demonstrate is, first we are going to take the expression for the feedback expression. So gain with feedback. So gain with feedback is given as what? AF will be equal to A divided by 1 plus A into beta whole square. So in this expression you can say, so the AF is nothing but gain with feedback, and A is nothing but open loop amplifier gain. So whenever there is a change in the amplifier, so what we are going to prove is, whenever we are going to see the small change in the amplifier performance, or which is changes in a way, so the feedback is not going to drastically change. So feedback gain will be unaffected. That is what we are going to prove. So for that, what we are going to do, first take the feedback expression AF, that is A divided by 1 plus A into beta we will be taking, and then we are going to take a differential on the both the sides. So both the sides with respect to amplifier, because we are interested in changes that occurs in amplifier, because beta is kept constant. So beta is kept constant, so assuming beta is constant means we are not worried about that beta. So because beta will be fixed, because the feedback network comprising of feedback network will be comprising of only passive components, and it will be assuming that feedback components will be not affected with respect to the main amplifier, because amplifier will be having small changes also, it is going to provide a difference in the output voltage you can expect, so that feedback is network will be having a constant. And then when we are going to take the differential on the both the sides, that means there is small changes that will happen. So you can say that with respect to A, so amplifier, if you are going to find out the difference, taking differentiating with respect to A, differentiating with respect to A, if you do, so then you'll be getting 1 over 1 plus A into beta whole square you'll be getting. So in this one, so after that, so for this given expression, for this equation 5.7, so now if I am going to divide the both the left hand side as well as right hand side with respect to AF. So with respect to AF, so DAF divided by AF across the left hand side, which will be equal to dA divided by 1 plus A into beta whole square divided by A into 1 plus A beta. So if you do that, so A will come to the denominator, and A 1 plus A beta, it will come to the numerator. But it will have 1 plus A beta at the numerator and 1 plus A beta into whole square it will be there. So you will be getting this as the final expression. So this expression suggests what? So if there is any change, small change in the current, so small change in the amplifier, this is dA by A is nothing but rate of change of amplifier. Okay, so this is what the rate of change of small change in the feedback amplifier and the small change in the amplifier, that will be given by this expression 1 over 1 plus a beta. So this indicates what? So whenever there is any changes, so any changes in the amplifier that takes place with respect to amplifier will have a negligible effect at the feedback gain. So negligible effect on the feedback gain. So when you see the on employing the negative feedback, you can observe. So if there is any changes that occurs due to the amplifier, will have this one. So upon feedback, you will be having 1 over 1 plus a beta. So you know that 1 plus a beta is will be very much greater than 1, so that you can see 1 over 1 plus a beta times it is going to, if there is any small changes occurs, it is going to have this much impact, 1 over 1 plus a beta. So that indicates what? So if on having any small change in the amplifier, so if I want to see the sensitivity, so sensitivity means what? So dA by A divided by DAF by AF, which if you can see, so you will be having 1 plus A into beta, which will be the sensitivity parameter. So it is going to have a least sensitivity with respect to that of change in the amplifier. So that is what you are going to prove over here. So next thing is, so next important property which you are going to find in bandwidth extension. So on employing the negative feedback, so the bandwidth of the amplifier is going to increase when compared to the normal amplifier bandwidth. So if we employ negative feedback, then the bandwidth of the amplifier will be still going to be increased. So that is what the property bandwidth extension. So for that we are going to consider an amplifier. Okay, so consider an amplifier. So we have already come across with the frequency response of amplifier, right? So we know that high frequency response as well as low frequency response, everything with respect to amplifier, with respect to common source amplifier we have seen. So in common source amplifier, for low frequency response of common source amplifier we have seen, along with that high frequency response of common source amplifier also we have seen. So we know what is actually the amplifier response, and first thing we are going to consider here is consider an amplifier. Here we are going to demonstrate how the bandwidth is going to extend. For that, we are going to consider an amplifier without any feedback. What will be the bandwidth of an corresponding amplifier? So we need to see first, and then upon applying negative feedback, so how the bandwidth is going to increase, we need to prove it. So first we are going to take consider an amplifier. So first we are going to consider an amplifier whose high frequency response is characterized by single pole, and its gain at mid and high frequency can be expressed. So we know that single time constant network, through the single time constant network, we know that high frequency response corresponds to R and C component, which will be having the which type of response it will be. So it will be having the which type of transfer function. So high frequency response of any amplifier will be corresponding to low frequency, low pass type single time constant network. That is low pass type single time constant you will be having. So that will be given by what? K divided by K1 plus S by omega S. So that is the transfer function. So same way here also we are going to find the amplifier whose high frequency response we are going to write. So amplifier A of S is nothing but the amplifier with respect to frequency, complex frequency variable. S is equal to J omega. If I substitute S is equal to J omega, then it will become depend upon the physical frequency. So A is nothing but amplifier. So amplifier with respect to frequency response we are going to write. So we are going to write in with respect to complex frequency variable A of S will be equal to midband frequency. So gain of the gain which you are going to get with respect to amplifier will in the midband, that is nothing but a constant AM divided by 1 plus S by omega H. This will be the 3 dB frequency for a given amplifier. On the amplifier again, omega H will be the 3 dB frequency, right? So omega H corresponds to the 3 dB frequency. So this is for what? So this is for high frequency response. So high frequency response only. So what will happen? So it will be having a low pass type of transfer function. That is what we are going to write here. So what is the AM corresponds to what? So that is nothing but the midband frequency gain, midband gain, and omega H corresponds to what? So omega H corresponds to higher frequency, that is 3 dB frequency. Okay, so that is the upper 3 dB frequency. If you find the 3 dB frequency, then easily you can find out the bandwidth. So bandwidth corresponds to what? So fh minus f naught. So f naught is nothing but the initial frequency, f0. F0 will be the initial frequency and fh will be the 3 dB frequency. So if you calculate that the difference between fh and f0, so that is frequency, so you will be getting the bandwidth of that corresponding amplifier. So in this case also you can say that for a given amplifier without any feedback, so omega h is the 3 dB frequency, and omega h is the 3 dB frequency. So now we need to find, so on application of negative feedback what will happen. So this is without application of negative feedback. So the amplifier is going to have a 3 dB frequency as this one, and the transfer function of this is given, and the 3 dB frequency is just omega h. So now when you apply negative feedback, so when you employ negative feedback, so with the frequency independent factor beta, so beta will be independent of frequency because it is made up of a passive component, and it is not assuming that it is a frequency independent factor beta if you are going to have, then around the amplifier. So AF, so the gain which you will be getting is nothing but what? So that is the gain which you are going to get with the feedback is AF. AF will be equal to what? A divided by 1 plus A into beta. So you can see AF, which is also nothing but a frequency dependent parameter. So because it is going to have amplifier along with the feedback network, whereas the feedback network is not frequency dependent. So only amplifier, main amplifier is frequency dependent. So why we are going to take this, this feedback gain, so that when we employ negative feedback means the gain which you will be getting is nothing but negative feedback gain. So that is the feedback with gain with the feedback, which is denoted as AF, and it is also depend upon the frequency term because it is going to have an amplifier term over here, that is depend upon the frequency, whereas beta is not dependent on frequency. So you can see AF of S, so it will be equal to A divided by 1 plus A into beta, whereas A depends upon the frequency, so we are going to have S term. So complex frequency term, variable term will be there. So in the denominator also beta times of S. For beta it is not there because we have considered a frequency independent factor beta. So it is not dependent upon frequency, so it is going to have only beta, just like a constant. A of S and A of S in the numerator. So now if we see, so just substitute what is A of S over here. A of S is given by what? So this is the expression AM divided by 1 plus S by omega h. So substitute the same thing. A of S will be AM divided by 1 plus sorry, so if you substitute here, so A of S will be equal to what? AM divided by 1 plus S by omega h, and then if you simplify, so I have just simplified that expression. I will just show you. So this is A of S. So A of S is given by AM, that is the midband frequency gain, divided by 1 plus S by omega h. So this is the main amplifier gain, and feedback. So gain with feedback is given by this expression. AF of S will be equal to A divided by 1 plus A into beta, A of S divided by 1 plus A of S into beta. So substitute the value of A of S as what? This expression. So AM divided by 1 plus S by omega h in the numerator term. So this has been written as AM divided by 1 plus S by omega h, and 1 plus beta into A of S, beta into AM divided by 1 plus S by omega h. So if you simplify this, so you can say, so AM divided by 1 plus S by omega h as this one. At the denominator, take it as common, 1 plus S by omega h as over here, plus AM into beta, and denominator 1 plus S by omega h, S by omega h get cancelled, and I am going to take AM as a constant over here, and then 1 plus AM into beta, I am going to take it as a common in the denominator. So if I take 1 plus A into beta, AM into beta, so this will be the resultant expression, okay? So 1 plus S by omega h plus AM into beta will be the denominator expression. So if I'm going to take 1 plus AM into beta as a common means, so here we'll be having 1 as it is, 1 plus, and S by omega h as it is, and in the denominator it will be having 1 plus AM into beta. So if you simplify this again, you'll be getting same. See, 1 plus AM into beta into 1 is what? 1 plus AM into beta, and 1 plus AM into beta into S divided by omega h into 1 plus AM beta. So AM 1 plus AM beta, 1 plus AM beta will get cancelled, and the resultant thing will be S by omega h as it is. So this is how we are going to write simplified expression. So now if you see here, AM divided by, so this is the feedback gain with feedback. AM is the midband frequency gain, divided by 1 plus AM into beta is there. So 1 plus AM into beta is there. So 1 plus S by omega h into this one. So this transfer function, so assume this as a constant, because for a given value beta is constant, for a given frequency, midband frequency gain, you will be treated as constant. So you will be having a transfer function of what? This transfer function k divided by 1 plus S by omega h into 1 plus A beta. So that means you can see the frequency, 3 dB frequency, which was earlier it was just equal to omega h, s by omega h in the amplifier case. In this amplifier expression, am divided by 1 plus s by omega h. This was only equal to 3 dB frequency was there. For now, it is going to multiply with 1 plus a beta times. So now, so the in this feedback with gain, so you are going to increase the value of the 3 dB. So suppose you can assume that here, suppose omega h or the frequency factor was equal to some around 1 kilohertz was there. So omega h was equal to 3 dB frequency point was 1 kilohertz ಅಂತ ಇತ್ತು ಅನ್ಕೊಳ್ಳಿ. So 1 kilohertz, suppose it is a into beta is 100 means, so the now 3 dB frequency will be equal to 100 into 100 kilohertz it will be. So now the 3 dB frequency it is going to increase by 100 kilohertz andre. So obviously the bandwidth of the corresponding amplifier, so for the bandwidth of the corresponding amplifier is going to increase. So now you can generalize the equation. Now in this figure you can see, so this is what the figure frequency response. So this is the midband gain. Okay, so this is denoted as what, am, and this will be the higher frequency response, and this is the low frequency response. Okay, so now before, without any feedback, so the 3 dB frequency it will be equal to what, omega h, omega h ittu. So this is the 3 dB frequency without feedback. So now omega h into 1 plus a beta multiply ಮಾಡಿದಾಗ, so what will be the frequency, 3 dB frequency has moved to this point. So now if you want to know the bandwidth from here to here, suppose you assume this is a high frequency response andaga, so you should neglect all these things, so this will be not there. And from 0 frequency at 0 till omega h, so if you take omega h minus 0 frequency, that gives the bandwidth. Now omega hf has been increased by a factor of 1 plus a beta, so now the new 3 dB frequency it is over here. So omega hf minus 0, so you can see the 3 dB frequency of this with feedback, and this is 3 dB frequency without feedback. So this will be increasing. Obviously omega hf is very much greater than omega h, so this indicates what, so bandwidth has been increased by a factor of 1 plus a beta. So when you employ a negative feedback, so when you employ a negative feedback, so the 3 dB frequency has been increased to new higher value, so that will be greater. So that what is the bandwidth for the with feedback, so bandwidth has been increased, so that is nothing but bandwidth has extension, bandwidth extension, that is what important property. So now, so omega h is nothing but so it has been increased by a factor of 1 plus a into beta times multiply ಆಗಿರುತ್ತೆ. So this is the new 3 dB frequency, so that is to have omega h multiply with 1 plus a beta. So whereas here omega hf will be equal to just equal to omega h, whereas here it will be 1 plus a beta times it is going to increase. At the same type, so lower frequency response ಮಾಡಿದಾಗ್ಲೂ ಸಹ, so if you find the lower frequency response, so the lower frequency response if you do also, so it is going to reduce the 3 dB frequency by a factor of 1 plus a beta. So here how the higher frequency, so 3 dB frequency has been increased by a factor of 1 plus a beta. So lower frequency it is going to, suppose the transfer function, if you are going to take it as a low frequency transfer function, that means low frequency transfer function andre eno, so this is the low frequency transfer function. So this low frequency transfer function, if it some amplifier, common source amplifier for low frequency amplifier if I am going to take, so for that also what is the amplifier, low frequency response amplifier anta tagondaga, so it will be omega L will be the 3 dB frequency. So this will be acting as a 3 dB frequency. So this is for a corresponding common source amplifier again, omega L will be the 3 dB frequency ಅನ್ಕೊಳ್ಳಿ. So omega h minus omega L corresponds to what? So bandwidth of this corresponding amplifier. So if you draw a 3 dB line which is going to intersect at higher frequency range as well as lower frequency range, so that if you calculate, if you draw a hard vertical line, so that corresponds to 3 dB for higher frequency area as well as lower frequency. So if you calculate the difference between omega h minus omega L, so that gives the bandwidth for that corresponding amplifier. So now for that common source amplifier, if I am going to employ negative feedback, then what will happen? So the transfer function, similarly how we have done over here, right? The same way if we do the 3 dB frequency in order to find out the lower frequency response if I am going to provide then the low frequency will be the new lower frequency will be having this much. So it is going to reduce the low frequency without feedback by a factor of 1 plus a beta. So 1 plus a beta times reduce ಆಯಿತು ಅಂದರೆ, so instead of here omega L, so the new omega LF will be over here. So this corresponds to what? So omega L compared ಮಾಡಿದ್ರೆ omega LF still it is going to reduce, so it will come towards the 0. So if you take the difference between omega HF minus omega LF, obviously the bandwidth of this new, that is a feedback gain with bandwidth with respect to feedback will be very much higher when compared to bandwidth without feedback. So this is bandwidth without feedback, and this will be the bandwidth with feedback. So you can see there is increase in the bandwidth, so that is nothing but the bandwidth getting extended. So higher frequency only, so it is going to increase by a factor of 1 plus a beta. So 3 dB frequency it is going to increase by a factor of 1 plus a beta. For a low frequency transfer function it is going to reduce by a factor of 1 plus a beta, so that overall the bandwidth of the amplifier is going to increase. Whether you understood or what? Hello. So whether you people have understood or what? So higher frequency, higher 3 dB frequency, it is going to increase by a factor of 1 plus a into am times of beta, whereas the lower frequency it is going to reduce by a factor of 1 plus am into beta. So this is how the bandwidth is going to increase when you employ the negative feedback. So, but when you observe, so whether you people are understanding or what? These are all very important points of the negative feedback. So that is about the bandwidth getting extended. So bandwidth extension I thought we have seen. So now we need to see the next important property of the negative feedback, that is the reduction of noise. So reduction of noise or noise reduction. So that is about how then on employing the negative feedback it is going to reduce the noise or it is going to increase the signal quantity. So increase the signal strength. So will be considered as a reduction of noise. So when noise and signal both are present in the given signal, so if you increase the signal strength, then obviously that is nothing but improving the signal strength. So increasing the signal to noise ratio is nothing but improving the signal quantity with respect to noise. So negative feedback can be employed to reduce the noise or interference in the amplifier. So what is better? So when you employ negative feedback, so the noise is going to getting reduced, it will get reduced. So that is for that we are going to prove now. So first we are going to consider this as a structure over here. So this is a amplifier without feedback. So this is an amplifier circuit without feedback. So we are going to compare amplifier performance with respect to signal and signal to noise ratio, and then we are going to again consider with for the feedback network, and then we are going to consider the signal to noise ratio for the amplifier with feedback. So we will see that how the signal to noise ratio is going to increase in this one. So now for a given circuit, assume that this is a circuit of an amplifier. So Vs corresponds to the signal voltage. Okay, Vs corresponds to signal voltage. Vn corresponds to the noise voltage. So this is nothing but a noise signal source, and this is nothing but a actual signal source. So this is going to both noise as well as signal source is going to club, and it will be given as input to the amplifier. And for this amplifier, it is going to provide output which will be having what? So signal to noise ratio. So output V0 will be equal to what? V0 will be equal to Vs by Vn. So we can see Vs by Vn. So this is nothing but output signal to noise ratio we are going to find. So signal to noise ratio. Signal ratio is given by Vs. Noise ratio is given by Vn. So signal to noise ratio is nothing but Vs by Vn. Okay. So something amplified output you will be getting over here. So that is nothing but Vs by Vn will be getting as the noise signal to noise ratio will be getting. So now coming to this one. So this is just an amplifier without any feedback. So now what we are going to do in the second case is, so we are going to consider to minimize this noise source, and hence you need to increase the signal quantity. So we are going to consider a feedback loop. So this is nothing but amplifier A1. So this amplifier A1 will be subjected to noise source Vn, whereas preceding to this amplifier, so this is the amplifier A1. So precise to this amplifier, we are going to connect one another amplifier which is of clean amplifier. For this amplifier, it will be not subjected to any noise. So this is clean amplifier. A2 will be considered as a clean amplifier for which we are going to give the input signal source. So if it is possible, assume that so preceding to the main amplifier, I am going to connect one an amplifier which is nothing but a clean amplifier for which I am going to apply the signal voltage. Okay, so signal voltage to the amplifier A2. Okay, so the output of the amplifier A2 will be subjected to given to the input to the A1 as well, and finally we're going to get the output over here. So part of the output will be given as given as input to the feedback network, and the output of the feedback network is given to the clean amplifier in this fashion. So you can see this is how you're going to see the feedback with the amplifier setup. Okay, so in this, so what I'm going to do is so I'm going to show through that. So the output of the signal to noise ratio should be greater than this output, means then it is nothing but we're going to achieve. So that is nothing but the reduction of noise itself. So what is going to happen is, so output will be given through the feedback network and it is going to give to the amplifier A2. So now first we need to see what is the output. So we are going to apply superposition theorem over here, because noise signal is given only to the amplifier 1, and that because of noise signal, so we are going to find out some output voltage. So along with the feedback network you will be getting some output voltage, and with respect to signals, voice signal, main signal, we're going to get some output voltage. So we are going to have a superposition, so one at a time we're going to consider. So first, if I'm going to find out only the Vn, so noise signal voltage means, so this Vs I need to short it up. So I'm going to just short it and I'm going to find out what is the output voltage with respect to only signal, noise signal alone. So Vn into A, so noise signal will be applied to what, so Vn into A1 divided by, so total loop, so total loop if you consider, so Vn into A1 will be the output, and divided by beta A1 into beta into A2. So that is what you will be getting with respect to noise. Vn is nothing but noise voltage into A1. It is applying only for a amplifier A1, divided by 1 plus total. So A1, A2, beta. So that is what the loop. So here it is A1 beta into A2. That is nothing but A1, A2, beta. So A1, A2, beta you will be getting. So this is the output voltage with respect to noise alone. So for the second case, this noise signal I am going to remove because it is a superposition. So by applying superposition, so in the second case, I'm going to remove this one, and I'm going to apply only Vs. So Vs when I am applying, so it is going to have what? Vs is applied for what? So A1, A2. So V0 will be equal to Vs into A1 into A2 divided by, so total. So this will be equal to what? A1 beta into A2. So this will be the total loop. So Vs into A1 into A2 divided by 1 plus A1 A2 beta. So this is because when you apply only the signal source alone, so this is you are going to get. When you are applying so only noise source, you are going to get this as the expression for the two expression. So together, if you sum up this expression, you will be getting what? So Vs followed by this expression plus Vn into followed by this expression. So both V out 1, V out 2 you are going to make. So that is going to be equal to V0. So now for this output voltage, if you consider the signal to noise ratio, so signal ratio, so this is the signal ratio. So Vs into A1 divided by 1 plus A1 into A2 into beta divided by noise ratio is nothing but Vn into A1 divided by 1 plus A1 into A2 into beta. So that you will be getting. So Vs by Vn, so if you substitute, so 1 plus A1 A2 beta, 1 plus A1 A2 beta, it will get cancelled, and A1 also get cancelled. Only will be left out with Vs divided by Vn into A2. So A2 will be what? So A2 is nothing but the amplifier 2 gain, that is a clean amplifier gain. So A2 multiply with Vs divided by Vn. So in the previous case it was just equal to, so Vs by Vn. So signal to noise ratio was just equal to Vs by Vn. So now the signal to noise ratio when employing this negative feedback, it has been increased to A2 times, it has been increased. So Vs by Vn into A2. So this corresponds to what? So the signal to noise ratio has been increased by a factor of A2. So on employing this feedback network and this configuration, so you are going to increase the signal strength. So without increasing the signal strength when compared to this open loop alone. So noise and signal both will be having affected over here. So now in this case, on employing this type of configuration, you're going to obtain reduction in the noise signal. So that is increasing in the signal has been taken place by reducing the noise. So this indicates what? So this is on employing the negative feedback, you are going to minimize the noise at the output. So that is how you are going to illustrate over here. So this is how you are going to illustrate. So A2 times higher than that of original case, Vs by Vn. So the improvement in the signal to noise ratio by application of feedback is possible only if, so you should remember, so this type of signal to noise ratio can be increased only when you have the assumption, that is the assumption is that so we are going to have a preceding amplifier to be connected before the amplifier A1. So if you provide this setup, then only you can able to show that signal to noise ratio is going to increase. So if only if it is possible to have a preceding the noise stage. So noise stage only there, second the first stage only noise is there. So preceding to that, so we are not having a noise stage, so that is A2. So preceding to the noise stage, we are going to have an amplifier A2, so that you are going to get the gain, that is a signal to noise ratio greater than that of original signal to noise ratio of an amplifier without feedback. So without this, without feedback, signal to noise ratio is small. With feedback, so the signal to noise ratio is increased by a factor of A2. This is how you are going to prove the sales in this in practical scenario. If you consider also when there is a when there is an audio amplifier, if it is considered at the output stage of the audio amplifier, so you will be getting some noise, hum, power supply hum. So when you increase or decrease the volume, and also you will get some noise, कोई ऐसा sound करता रहता है. So when you are so that is nothing but a power supply hum. So in order to reduce that power supply hum, what they are going to do, they are going to have a pre-fed amplifier, so that it is going to reduce the power supply hum. So small signal will be connected, small signal amplifier will be connected before to that of audio amplifier, so that it is going to reduce the noise signal, and that is going to provide a clean, so output will be able to visible, will be audible. So that is about the general common example, so that you can see in the power supply hum removal of power supply hum. So that is about to remove the feedback or noise signal. Okay, so with this, I'll just finish up today's class. So this is two important property which you study. One is the noise reduction, another one is the extension of the bandwidth. So bandwidth extension as well as the noise reduction. So these two are very important property. So they, among the four properties, they may ask in exam to demonstrate. So if they will be telling to explain how the reduction of noise will take place upon feedback, means you should be in a position to derive, and you should explain this one. Yeah, the same way they can individually they can they will be selecting and they will be telling. Okay, so you should be in the position. So in the tomorrow class, I will just do the another important property, reduction in non-linear distortion. So that if I complete, so I will be just completing about the properties, important properties of negative feedback. So any doubt is there? Whether people are understanding or what? Hello. Hello, students, whether you people are sleeping or what? Kavya, Chinmay, Umutavali, Ashrita,
Sir,
whether people are there or sleeping,
sir, no, sir, hearing, sir.
hearing. So I am able to hear your noise over there in the background.
Sir, no, my sister is working, sir. That's fine.
Okay, okay. Okay. Okay, thank you. So I'll just conclude today's class. So we'll meet you tomorrow.